It's great to see so many people in the room today. I want to talk today about parallelism, and particularly about how to think about parallel performance. So the Java class libraries have supported the ability to do parallel decomposition through the fork join library for quite a few years now. But in Java 8, we added something that makes it a lot easier to use parallelism, which is the streams library. And I think most of you have used streams before, right? Great. So what I'm going to talk about today is not what streams is, but how to think about parallel performance and whether parallelism is going to help you or hurt you. Streams makes it easy to go back and forth between sequential and parallel execution, but we still have to think about which we want, and so that's basically the topic of today's talk. That's right. So this is how you know I work at Oracle. I have to give this disclaimer slide. Not an imposter, real Oracle employee. See, legal slide. Okay, great. So everyone's probably seen this graph, right? So this is a graph that Herb Sutter put together almost 10 years ago at this point, and it shows a number of trends in processor hardware. So the green line, this is plotted on a log scale. So the green dots show number of transistors on a chip over time, right? So since this is a log scale, a straight line means something that's exponentially increasing, and this essentially says, yep, Moore's law works. It's continued to work over a relatively long period of time. Transistor counts are consistently doubling every 18 months. But what changed, and you can sort of see that from the lower graphs, is what we got out of those additional transistors. So around 2002, 2003, something very unfortunate happened, which was hardware engineers were unable to plow that transistor bounty into giving us just faster and faster chips. So for the longest time, we were able to make our programs faster just by dragging our feet and waiting to run it on the next generation of hardware. That was a great trick for like 25 years. Unfortunately, that trick doesn't work anymore, and so we have to actually do our jobs now. And this is demonstrated by these lower three lines. The blue line represents clock speed. So we saw clock speed increasing exponentially for years and years and years, and then it leveled off, and it's pretty much stayed where it is. The lower two measures are other measures of performance. The light blue line is power consumption. So as chips got faster, they were consuming more power, and we basically hit the limit of how much power we're willing to feed into chips for cooling reasons mostly. And the bottom line, the purple line, is an interesting one. It shows a measure of parallelism inside the chip, how much work we're getting out of the chip per clock cycle. And again, hardware engineers were able to do really cool stuff in terms of using parallelism within the chip to give us faster performance, and that game played out, in 2002, 2003 time frame as well. So all of these forces basically conspired to say chips aren't getting sequentially faster. It took from 2003 to maybe 2007 or 8 to get over the period of denial that followed. We were kind of all hoping the good times were coming back, but they weren't coming back. But it doesn't mean that Moore's law has been repealed. We're still getting more and more transistors every year. So what are we doing with them? We can plow them into more cores on a chip rather than faster cores. So we're still getting better chips, but we have to work harder to use them because we have to figure out how to parallelize our software to run on many core chips. So if you look at the chips that the electronics industry has actually delivered, if we went by what Moore's law said, the number of cores we would have would follow this red line. But in reality, the blue dots indicate high-end chip core counts. These are the Intel EX Xeon chips. They are increasing, but not nearly as fast as Moore's law says they can increase. And the basic reason for that is economic. No one wants to buy million-core chips because we don't know what to do with them. Or the set of applications that know what to do with them is small enough that there isn't really a market for it. So instead of seeing 1,000-core chips today, we're seeing high-end chips with 20, 40, 60 cores, but not 1,000, 2,000, 4,000 cores. And of course, consumer chips have even lower core counts than this. So the multi-core age is here, but not as dramatically here as it was predicted it would be 10 years ago. And I think that's largely because of us. There isn't demand for these chips. We don't know how to use them effectively. Okay, so Concurrency isn't an end in itself. It's a means to an end, right? And it's a means to better performance, and in particular, it's a means to better processor utilization. Now, what that means has changed over time, but for the most part, we tend to use concurrency as a way of getting more performance out of the hardware. There are some programming models that take advantage of concurrency actively for structuring a program, like actors, but that's still sort of in the fringes. For the most part, we view concurrency as a tool for squeezing more performance out of the hardware. And the strategy that we use changes over time as the hardware changes. So back in the single core era, we used concurrency to get asynchrony, to do non-blocking operations, do useful work while we were waiting for an I/O to complete. When chips had a few cores, we tended to focus on sort of coarse-grained task-based concurrency. So we had thread pools where you'd be running, a handful or a few dozen tasks simultaneously. And this was largely about improving throughput, processing more requests per second out of your, 4-core server box. As core counts increase, another target becomes available, which is using parallelism not to do more work on the same box, but to get to the answer faster. So throw more cores at the problem in order to get to the answer in a smaller amount of wall clock time, because maybe having the answer faster has business value. Right? So the techniques we use sort of follow the hardware trends, and this makes sense, right? The hardware guys cook up some cool new hardware stuff, and then the software guys have to figure out how to use it effectively. And that starts with the operating system, and that works its way all the way up the stack, through the JVM, through the language, through the libraries, through the programming model. And so, the hardware is out there on the leading edge, and languages, libraries, and frameworks are kind of trailing. And so, in 1995, it was fairly cool that Java had built-in support for threads and locks and conditions queues, built into the JVM, built into the language. That was kind of a new thing at the time. And that was relevant to the concurrency that was available from the hardware of the day. When we started to see multi-core systems, that's when the Java libraries acquired tools like thread pools and blocking queues and concurrent collections. And when we started to see more cores, that's when the libraries acquired tools for task-based parallelism, and as the hardware has continued to improve, we try to make it easier to access the power of the hardware. Okay, so I want to spend a second on terminology. People often use the words concurrency and parallelism interchangeably. They're not the same thing, and unfortunately, the historical meanings of concurrency and parallelism that have grown up in the literature, I don't think are actually as useful today as they were when they were originally coined. And so a lot of modern curricula are sort of redefining these terms, which makes it even more confusing. So the historical meaning was that concurrency is a property of a program structure. Whether things could be happening at the same time, whether your program is structured as cooperating activities, whereas parallelism was historically framed as a property of the program's execution. Do things actually happen at the same time, or are you just doing fancy scheduling tricks? So in the old model, concurrency was the potential for parallelism, and this was a useful distinction in the older days when true concurrent execution was mostly a theoretical construct. But I think it's less of a useful distinction today. So the distinction that people are, that educators are using today is to say that concurrency is about correctly and efficiently controlling access to shared resources. So this is things like constructing thread-safe data structures like concurrent hash map, and the primitives of concurrency are things like locks, events, semaphores, coroutines, software transactional memory, etc. It's about coordinating access to shared data, whereas parallelism is more about using additional resources to get the answer faster. I could do this with one core, but if I had 10 cores to throw at it, maybe I can get it faster. If I had 100 cores to throw at it, maybe I could get the answer even faster. So, all right, this may sound like an academic digression. Why should we care about this distinction? Well, the reason the distinction is relevant is it turns out that concurrency is usually pretty hard. That the tools that we have for concurrency, like locks and threads, requires complex reasoning that's like easy to get wrong. And even if you have the secret wizard spell book, it's still hard to get it right. Whereas parallelism tends to be really easy. at least in terms of the way you think about it, because parallelism, the standard trick in parallelism is partition the problem into two smaller problems, and then work on the problems independently. And then when you're done, combine the results. And this is how we effectively share work in the real world, right? If you've got a stack of papers to grade, well, you call in your teaching assistants. You give them each 1/nth of the stack. You go to lunch and let them do the work, right? And they don't need to coordinate with each other while they're grading the papers. And then, in the end, they just make a big pile, and you've gotten your work done very efficiently. So it doesn't require a lot of reasoning as long as you partition the data and partition the work into independent tasks. So parallelism tends to be much easier than concurrency. People are scared by concurrency, rightly so, because it's hard. Parallelism doesn't have to be hard. So it's worth noting that parallelism is strictly an optimization. It's about using more resources to get the answer faster. If you don't have additional resources, you just have one core to work on, no problem. You can still compute the answer sequentially. It just might be slower. Now, the flip side of parallelism being an optimization is that it's only useful if it is actually an optimization, which is to say it actually gets you the answer faster. And it isn't necessarily the case that using more resources gets you the answer faster, or even as fast. So there are some parallel computations that are slower than the obvious sequential alternative. So that means we have to think about it, unfortunately. But that's not hard. We have tools. We can, we have analysis. We can look at the problem, think about the problem. We can implement, measure, test, repeat, et cetera. A general rule of thumb, this is one of the questions that that comes up on Stack Overflow all the time, is like, okay, Java has parallel streams. Should I use parallelism everywhere? No! Start with sequential streams. And then if you need to optimize your code because you're not getting to the answer fast enough, or fast enough is defined by actual performance targets and business requirements, then you can think about whether making it parallel will actually get you a speed up. And the way we measure the effectiveness of parallelism is by speed up. How much faster is the parallel execution, or slower, than the sequential execution? Okay. Now, it's worth keeping in mind that a parallel computation is always going to do more work than the best sequential alternative, because it still has to solve the problem, and it has to do extra stuff to manage the parallelism. Split up the work, hand it out to workers, wait for the workers to finish, combine the results. That's extra overhead on top of actually solving the problem. So the parallel version always kind of starts out at a deficit against the sequential version, and you're hoping to make up for it in volume, right? So if you have 20 papers to grade, going out and finding 20 people to do the work, talking them each into doing one paper, probably takes longer than grading them yourself. So you have to have enough volume, and you have to have a parallelizable problem, and you have to have a good parallel implementation in order for this to win, right? So what most of this talk is about looking at a problem and developing an intuition about whether parallelism is likely to help you or not. Of course, you still want to measure on top of that, but a lot of problems you can look at and say, that's not going to parallelize because not enough data, there's an inherent bottleneck here, et cetera. So I'll go through all the examples of things that, that can deprive you of parallelism. So as an example, to start with, you have to have a problem that's parallelizable to begin with. Some problems are inherently sequential by their definition. So here's a pair of functions. G of 0, you have some operation f, okay? And then you're going to define g, where you're saying g of 0 is just f of 0, and g of n is f of g of n minus 1, okay? And similarly, I have another function whose definition looks almost the same, but actually has different parallelism characteristics, and I'll go through it. But it's worth pointing out that even though they're both defined recursively, they have very similar structure, the left one is inherently sequential and the right one is not, and I'll show how that works. Okay, so let's take the first one. Parallelism is going to be a lost cause on this, because if I rewrite my function, g, as an iterated function, what I realize is that g of n is basically f of f of f of f of f of 0 with n applications of f. And I can't start computing f of 0 until I've computed f of 0, right? The problem is fundamentally sequential, and if I draw a data flow dependency diagram, well, g of 0 depends on f of 0, g of 1 depends on g of 0. You look at that and you say, that's just not going to parallelize, right? So some problems just don't parallelize, and so it's worth recognizing that. If you're lucky, you try to implement this in parallel, it will be no slower than the sequential implementation. That's the best case for a non-parallelizable problem. All right, so let's look at our other example, which looks almost the same, especially if you don't like math and all you see are F's and G's and recursive definitions and all that. This problem turns out to be very parallelizable because if we draw the data flow dependency diagram, we see, okay, h of 0 depends on f of 0. H of 1, well, it depends on h of 0, and it also depends on f of 1, but I can calculate f of 1 and f of 0 separately because they have no, they don't depend on anything. And at each level of the tree, there's, I can get some parallelism because I can be calculating all of these f's simultaneously, right? So if you draw out the data flow diagram, it gives you a very quick hint as to whether the problem that you have is going to be amenable to parallelization or not. If you rewrite h, you realize that h of n is just adding up a bunch of independent things, and addition parallelizes nicely. And computing those f of 1, f of 2 also parallelizes nicely. Right? So there should be some ability to extract parallelism from this problem. In fact, this is what we call an embarrassingly parallel problem. But it is possible to write the solution in such a way that we get in the way of extracting the parallelism. So step 1 is you have to have a problem that's parallelizable. Step 2 is that you also have to have an approach for extracting the parallelism. Okay, so like I said, these two functions look similar. One was parallelizable and one was not. So let's look at how we might actually express the computation of this to, to exploit the possible parallelism. And the key takeaway in this section is we all have some bad habits. We have some bad habits from having written sequential code for 10, 20, 30, 40 years, depending on how long you've been programming. And we have to unlearn those bad habits in order to effectively write parallel code. Okay, so again, let's take a simple problem. This is basically what the h function is. Add up the numbers from 1 to n. So, what kind of data flow graph do we get out of that? Well, let's write up an implementation. Here's a sequential implementation where we have a sum counter and a for loop where we where we increment our counter. Well, if we write it out this way, we're not calculating the sum. We're essentially calculating the sum sequentially, and so we end up with a computation tree that looks like something like this. Now, that's not the computation tree we want, but that's the computation tree we get out of a typical sequential implementation. The computation tree we want is something that looks more like this, where you do a bunch of additions in parallel, and then the next level up in the tree, you do more additions in parallel, and it's only when you get to that last operation where you have two pieces to add that you end up being sequential, right? So one of the patterns that we have to unlearn that gets in the way of writing parallel-friendly code is this accumulator pattern, right? As soon as you start with int sum equals 0, you're already dead. Right? Because you've already created a bottleneck that every task is going to have to contend for access to that sum. So whenever you see code like this, that should be a warning sign. This is we call this the accumulator anti-pattern. This is going to get in the way of parallelism. So, all right, well, how would we solve this problem, not sequentially? Well, we could try it with concurrency. Here's a broken example here. But it illustrates, part of the challenge of having this accumulator variable where we say, okay, I'm going to whack the array in two pieces. So I have a left half and a right half. And I have my sum accumulator. And then somehow concurrently, magically, sprinkle the magic concurrency dust. I'm going to, sum up the first half and the second half of the array concurrently. And they're both trying to update the same accumulator variable. What's going to happen here? Right? This is broken. Right, because we have a data race. Both of these concurrent activities are trying to both read and write this shared accumulator, and you're going to get the wrong answer, Okay, well, we know how to fix that, right? We can make sure that we do this atomically. And how do we do this atomically? Well, we take a lock. Well, that kind of makes the code correct, but our performance is going to be even worse than the sequential version, because now every time someone goes to add a number to a counter, they have to take a lock. And, well, it's almost guaranteed that the other guy has the lock, so they're going to spend a lot of time waiting for the other to give up the lock, and it actually takes a fair amount of time to release a lock to another thread. So you have this tiny, tiny amount of work to do. You want to add two numbers together. You take a lock, which dwarfs the amount of work, the amount of time it takes to do the addition. So we have a solution that's correct, but is actually worse than the sequential version. So, all right, so where are we? Well, we had a problem that was embarrassingly parallel, but we tried a couple of ways to exploit the parallelism, and we failed. All right, well, let's keep trying, if at first you don't succeed, right? So, but I'll step back. The fundamental problem, with the broken examples is shared state. The first version was broken because it didn't coordinate access to the shared state. The second version sucked because it coordinated access to the shared state, but we lost all our performance. So there's, three ways to safely handle shared state: either coordinate access using locking, don't share, or don't mutate. Generally, the first two, don't share or don't mutate, are a lot easier to get right than the third. So let's try the don't share approach. Let's do the same thing we did before. We partition the array into two chunks. We'll operate on them separately, but we won't have any shared state, right? So here's a first cut at a parallel solution. It looks almost like the other one, but this one actually works because the first task is busy incrementing the left sum. The second task is busy incrementing the right sum. They're not accessing a shared counter, so there's no need for coordination. There's no contention. We get the right answer, and then when it's all done, we add the two together, and everything's good. So this is, this is basically the game with parallelism, where you want to divide the problem into generally two pieces. You want to have each piece work on their part of the problem independently without having to access either shared inputs or shared outputs. And that way, they can each work efficiently on their part and, get to the right answer. So decompose the problem into subproblems, solve the subproblems, combine the result, hopefully with no sharing and no contention. So, all right, how's this going to perform? Well, if we have enough data, then we'll overcome the overhead of forking off these concurrent tasks, waiting for them to finish, and joining them. And we'll probably get a pretty good speed up, if we have two cores. We probably won't lose very big if we have one core. It'll just run the tasks, one ahead of the other. But the only thing we lose is the fixed overhead of dividing it. But given the structure of this program, it's pretty obvious that if we had 100 cores, we're still only going to be able to use 2 of them effectively. So we've made progress. Potentially, we could double our speed with enough data, but we'd like this to be able to scale to many cores, right? So let's see how we would, how we would extend that. So the basic game for parallel execution is, the old trick, divide and conquer. You recursively divide your problem into smaller problems. So you take a big problem, divide it into 2 smaller problems. If those smaller problems are still kind of big, you divide them again into smaller problems, and you keep doing them until they're small enough that the logical thing to do is to solve the subproblem sequentially, right? So if I'm asking you to add up 2 numbers, you're not going to fork off 2 tasks. You're going to say, adding these numbers is so little work that I'll just do it sequentially. So when you get down to a small data size, it's generally more efficient to do it sequentially. So recursively divide the problem until the chunks are small enough, solve the chunks concurrently, hopefully with, they're independent, and then combine the results. So this is a pseudocode. Is the problem small? If so, solve it sequentially. Otherwise, concurrently solve the left subproblem and the right subproblem, and then combine the results. This is basically all parallel programs have this behavior. The nice thing about this is it's simple, right? How many cores I had wasn't an input into that code. So it wasn't an input into writing the code. It's an input into running the code. And a lot of problems, a lot of data structures are already defined recursively, right? Like trees are defined recursively. So you're already going to be operating on them recursively anyway. So it's a good match for a lot of data structures anyway. There's no shared mutable state because even though they're reading data out of the same array, they're just reading, they're not writing. We don't have to coordinate for that. The intermediate results, like those intermediate sums, they just live on the stack. So this has the potential to be very efficient. Of course, devil in the details, right? How expensive is it to fork off a task? How expensive it is to wait for a task? These all affect what kind of speed up you're going to get. Generally, because spinning up tasks, especially at the early stages of a program, has some cost, you want to be able to start breaking off work early to start some worker working on some subpart of your problem while you're still decomposing the rest of it. But the decomposition should be dynamic, and it can incorporate how many cores do I have, what's the load, and that's exactly what the fork join framework that we added in Java 7 does. It manages the decomposition of tasks and the waiting for tasks and all of that, so you only have to write the part of your program that has what problem am I trying to solve, and the mechanics of creating tasks, merging tasks, handled by the library for you. To draw a very simplistic picture, if I have an array of numbers, I want to add them up. I could add them up sequentially. If I only had 8 numbers, that would be the logical thing to do. But imagine it's a much bigger array. So what am I going to do? I'm going to divide it into 2. I'm going to divide that into 2 again. And I'm not copying the data. I'm just sharing the reference because my tasks are only going to work on their little part of the problem. And then this turns into a bunch of little add up 1 and 2, add up 3 and 4, add up 5 and 6, add up 7 and 8, and because addition is associative, I can do that in whatever order I like. And then I compute the partial sums, and I work my way up the tree until I have my answer. So it actually does work like that, right? It's fairly straightforward, and it's easy to reason about because everyone works on their little subset of the data. Okay, so this all sounds great. How does it work in practice? Well, sometimes it works great in practice, sometimes it doesn't. How do we know whether it's going to work great or not? Well, we could measure, but before we measure, we could think about it. So that's what I'm going to talk about. What are the costs in doing that parallel decomposition? Well, sometimes there's a cost of splitting the problem in 2. Some problems are much cheaper to split than other problems. Sometimes splitting is so expensive, it's easier to just do the thing sequentially. If you have to copy a lot of data to split the problem, that becomes an impediment to parallelism. There are the task-based costs, forking off tasks, joining with tasks. You can do a lot of work in the time it takes to do a handoff across threads. So you don't want to spend all your time managing tasks. You want to spend your time keeping those cores busy doing actual work. On the other side, there's some cost to combine the results. Some combination operations are cheaper than others. If, in the example I gave where we're summing an array, the combination operator is take the sum of the left half and the sum of the right half and add them. That's a very cheap combination operation. But what if the result of the subproblem was a set and I had to merge the sets? That's a much more expensive operation, right? So just like splitting cost, combination cost can also be an impediment to parallelism. And then the elephant in the room is that pesky hardware. Hardware locality tends to be a significant factor in determining whether we get parallelism out of a problem or not. And when I say hardware memory locality, I mean is the data that a given task is working on located close to the other data that it's working on in memory? Because if it is, it will be hot in cache already, and when the task goes to get the next item to work on, it's not going to be waiting on the memory subsystem to cough up data. If you have a data structure that exhibits poor locality, you may divide it up into a whole bunch of worker threads, but then what's likely to happen is the worker threads are going to spend all their time waiting on the cache subsystem to deliver the next piece of data to operate on. And most systems are memory bandwidth limited, they're not CPU limited. And so if you've got a lot of cores, all cache missing at once, you're not going to get a lot of throughput out of it. So each of these factors steals away part of the potential for parallelism. So if you analyze your problem and you say, are any of these particularly bad, you're likely to get poor parallelism out of it. And in general, you need a fair amount of data for parallelism to work for you. If you're adding up 1,000 numbers, do it sequentially, it's much faster. But if you're adding up 1 billion numbers, parallelism is going to give you a big advantage. Okay. So like I said, Java SE7 adds the fork join framework. This is a task management framework designed for fine-grained, mostly CPU-intensive tasks. Doesn't mean you can't use it with I/O, but it's tuned for CPU-intensive tasks. The nice thing is it scales really well over the range of cores that you're likely to encounter on a real system. And so you don't have to worry about the details of task management, and it's basically optimized for the kind of divide and conquer algorithms I've been showing. So the two basic operations are fork off a task and wait for that task to complete, fork and join. And that's an efficient implementation of that magic concurrent primitive that I was showing in my earlier examples. The overhead isn't 0, but it's pretty good. All right, so let's talk about streams. We talked about how you've got the stream framework. It's pretty cool. People like it. It gives you almost free parallelism in terms of making it really easy to express that I want this computation sequential or parallel and to flip back and forth between them. So that's great. And it encourages a sort of more declarative style that, of programming that tends to be more readable and less error prone. So that's great. But it's not magic parallelism dust. And so you still have to know, is this going to execute efficiently in parallel? Otherwise, you can easily say dot parallel, and maybe it's not any faster, maybe it's even slower. Okay, so you've all seen examples like this, right? You have imperative code like this. You can turn this into a stream pipeline, and yay, the code is smaller, it's more compact, it's easier to read. But the important thing is it's declarative. It's telling you what answer you want rather than how to get to the answer. And the benefit there is it's much easier for the library to say, I know how to do this in parallel. I'm going to go decompose it for you. There's basically no compiler that could parallelize that first example. But parallelism is the bonus. It wasn't the point of doing this. The point of doing this was writing code that's easier to read, less likely to be wrong, but it's a nice bonus that the runtime can optimize it for you as well. Okay, so before I gave a bunch of criteria of things that steal away your parallel performance, splitting, combination, task dispatch, and locality. So each of those apply to a parallel stream. The parallel streams work by splitting their data sources. So the first question is, well, what's the source for my stream? Is it an array list or a linked list? And these split very differently. An array list splits really nicely. You just compute the midpoint and say, you work on that half, you work on that half. Whereas a linked list doesn't split so nicely. How do you split a linked list? First and rest. Well, you could do that again recursively, right? You have first, and then first of the rest, and rest of the rest. And you can keep going. And you actually could get some parallelism out of this if the task you're doing is sufficiently expensive, right? If you're doing some really expensive, cryptographic attack, you actually could get some parallelism out of a linked list. But if you're just adding up, numbers or searching, searching a data structure for something, you're not going to get it, right? So splitting cost is a real concern. And so you need to know where's my data coming from and how well is it likely to split. Task dispatch, well, that's handled by the fork join framework. You can't do too much about that. The combination cost, though, is again part of your problem. Am I adding up numbers or am I merging sets? And then locality goes back to the source. What is my source? Is it an array? Arrays have great locality. Is it a linked list? Linked lists have almost pessimal locality, right? So you have to know where's my data and how's it laid out in memory. So I'm going to wave my hands and give you a completely unscientific model for thinking about parallel performance. I see Martin wincing when I say this. Imagine a really simple model where you only have two parameters. How much data do I have, and how much work do I do per data element? And where work might be, a basic arithmetic operation or a bytecode or a machine cycle. It doesn't really matter. But you're asking, am I just adding up numbers or am I, trying to factor large primes? And you multiply these things together and this needs to be larger than some threshold. So if you have a trivial little operation, like adding up numbers, you generally need on the order of 10,000 elements in order to get a speed up out of parallelism with, with this framework, which isn't unrealistic. We all have data sets that are much, much larger than that. So, but 100 numbers, not going to parallelize. 1,000 numbers, not going to parallelize. If your operation is more expensive, then you don't need as much data to get over this threshold. But if you have a trivial small operation and a trivial amount of data, just stop. Sequential's great, just use that. All right, so let me work through these, these items one at a time. Source splitting. Some sources split better than others. And the cost of splitting a source is, well, you have to compute what the split is, and you also have to take into account how even is the split. So an array list, or an array, you can find the midpoint really cheaply, and you're going to split it into almost equal pieces. That's great. And as a bonus, you even know exactly how big the pieces are, which helps you avoid copying in some operations. So that's great. So arrays are great. Linked lists have none of these properties. They split terribly. You have to take a pointer traversal to do the split. You come away with a terribly uneven split, 1 and n minus 1. If your data is not already in a data structure, but it's coming from some kind of generator, there's an analog here. So iterative generators, like calling an iterator to get your next element, that works exactly like a linked list. Right? Splitting an iterator is just like splitting a linked list. On the other hand, if you have a stateless generator, that splits just like an array does. So, depending on whether your data is already coming from a data structure or it's coming from a computation, you can still, looking at the structure of it, say, is this going to split well or not? So, and as a comparison, both of these streams generate the same, the same sequence, right? InStream.iterate, start with 0 each time, add 1 to it, and then stop after a certain number. That generates the stream 0, 1, 2, 3, 4, 5. So does InStream.range. But the first one parallelizes terribly. And the second one parallelizes perfectly, right? Because the first one is a sequential iterator, and the second one is a stateless generator. Okay, so it's real, they look the same. You look at that and you say, well, they compute the same sequence, but they parallelize very differently. Okay, so like I said before, the elephant in the room is locality. Parallelism wins only when we can keep the CPUs busy doing useful work. Waiting for cache misses is not useful work. And so if you have your data in an array, that's great, because everybody starts working on their little chunk of the array. But when you go pull in the first element, it's going to pull like the first 15 elements into your cache line. So fetching the second, third, fourth, fifth, sixth element, that's basically free. And as you sequentially walk through an array, the hardware prefetcher kicks in and says, you're probably going to need the next chunk of the array. Let me go start fetching that, so you're not going to have to wait for it for as long. On the other hand, if your data is scattered all over memory, you're going to be taking cache misses left and right, and you're going to be spending a lot more time waiting for data and a lot less time doing computation. And the comparison is, I have an array of ints, and I turn that into a stream, and I want to add them up. That's great, because I get great locality. This one, this one, this one, this one, I'm done. Whereas if I have a stream of boxed integers, in order to get the number that I want to add up, I have to take a pointer dereference to go find the payload of that integer box, and that's not likely to be in cache, so I'm going to have to wait for that, right? So the performance, again, these compute the same result, but the performance of the one that works on primitives is better, and the parallelism is going to be better as well, because you're going to be able to exploit the locality that the hardware gives you. And to illustrate this is how these things are laid out in memory. If I have an array of ints, they're all sequentially in memory, one after the other. So the cache is working for me, the prefetcher is working for me. If I have an array of boxed integers, every time I go to traverse one of those pointers, I risk taking a cache miss. All right, so locality is important. The trouble with locality is it doesn't really appear in your code, right? We don't have a locality keyword in our language. We just have to have some knowledge about how are our data structures laid out, and how is that going to affect our performance, if we care about performance. All right, a few other considerations. Some streams have what's called an encounter order. That means the the order in which the elements appear has some significance. Arrays have encounter orders. There's a first element of an array, there's a second element of an array. Whereas sets don't have a meaningful encounter order. They just have elements, which means the iterator is perfectly free to serve up the elements in whatever order it finds convenient. Now, some operations, their semantics are tied to encounter order. Operations like limit and skip and find first. Find first means find me the first element in the encounter order. That means you have to, you can't just pick any element, you have to pick the first one. Now, sometimes in our problems, the encounter order actually has a meaning. Sometimes it doesn't. Sometimes you just care about any element that satisfies a certain property. So we can't automatically guess what the meaning is, right, to you, but you probably know as the programmer, you have an idea what problem you're supposed to be solving. So if you've got a stream pipeline and you're using an operation like limit or skip or find first, think about, do I care that I'm limiting it to the first n elements, or do I just want to limit it to n elements and I don't care which? And if you don't care which is often the case, then you can say there's a stream operation called unordered, which means I don't care if you thought this stream had a defined encounter order. It doesn't. Just ignore it. And that will enable optimizations where limit and skip and find first will, rather than picking the first n, will pick any n. If you're using operations whose semantics are tied to encounter order, that limits parallelism, right? When you say compute the first n elements of this sequence, I can't bring as much parallelism to bear as if I say compute any n elements. Just start processing on a whole bunch of cores, and as soon as you have n, we're good, we're done. I can get a lot more parallelism out of that. So beware of operations that are intrinsically tied to encounter order. Ask yourself if it matters. If it doesn't matter, tell the system you don't care about that. Okay. We talked about splitting, we talked about locality, we talked about encounter order. Let's talk about result combination. In some operations, like if I'm trying to find the biggest number in a set or trying to add up the elements of a set, the merge operation is super cheap, adding two numbers, computing the max of two numbers. For other operations, if I'm doing a group by operation and I'm creating a hash map, merging two hash maps is really expensive. It involves a lot of copying, it involves sequential iteration through the key set, and not only once, but you're probably going to do this at every level up the tree, right? So if you split to, let's say, 4 levels, you'll do merging of the hash set at the bottom level, and then the next level up, and the next level up, and then at the top level. So that's a lot of work. You have to look at this and say, is this an expensive operation? Is this going to be an impediment to parallelism? If you do an operation like collecting to a hash set, and you try to do that in parallel, you'll often see a significant slowdown, 3x, 5x, 10x, because all the work you're doing is just combining, combining sets. Now, there's an alternative to that. You could either go sequential, or you could use a concurrent data structure. All of the operations that produce sets and maps, like group by and such, they have a concurrent analog where you can say, put the results in a concurrent hash map and just allow all the threads to fire elements into the map. This is a trade-off because you lose ordering. It's an intrinsically unordered operation, but you also ditch the bottleneck of merging your result set. So you have to ask yourself, what's my merge operation? How expensive is it? And am I paying for more than I need? Am I paying for an order-preserving merge when I don't need one? Right? So there's often a lot of ways to tweak your problem and say, well, I can get rid of some of these costs. Okay, so just to illustrate, if I have, if I'm trying to collect the elements 1 through 8, I can create a little set at the bottom, but then I have to merge them into intermediate sets, and then I have to merge them again at the end, right? And that's expensive. Okay. So I rattled off a list of factors: splitting cost, merging cost, locality, sensitivity to order. Each of these could undermine your speed up. And if any one of these is really bad, unless you have really expensive operations you're doing on each element, it's likely to be a significant impediment to parallelism. the good news here is you can look at a pipeline and say, how's that going to parallelize? And you can very often immediately look at it and say, yeah, it's not going to parallelize well because of this, which is great because you just saved yourself a whole bunch of measurement time and experiment time. You look at the problem and you say, it's just not going to parallelize well. So this should always be our second step. Our first step, run it sequentially. If it's fast enough, you're done. Go solve a different problem. Second step, if you think it needs to be faster, look at it and ask if parallelism is going to help you. And usually you can figure it out pretty quickly by applying these criteria. Only then do you want to move on to, well, let's try it in a parallel measure and see how it works. So summing up, streams are cool, yay. Parallelism is cool, yay. But parallelism isn't magic performance dust. Parallelism is hard. It's easy to ask for, but it's hard to reason about. We have to, it's only an optimization. We should only apply it if it actually delivers an optimization. And it may require analysis and measurement in order to figure that out. Now, I'll give a little commercial about performance, performance tuning that I always give, which is, if you're going to do performance tuning, first make sure that your code isn't already fast enough. What does fast enough mean? Look at your business requirements. If you don't have business requirements for performance, your code is fast enough. Because if you haven't invested in defining performance requirements and you haven't invested in defining performance metrics, which isn't easy and isn't cheap, then your code is fast enough. Done. Stop optimizing. So these techniques are useful, but but apply them when you already have a good reason to believe you need to speed up your code, and when you think when the analysis tells you that parallelism might actually speed up your code, and when your measurement tells you it actually does. All right, so I think we have a few minutes left. Oops, I think we have a few minutes left to take questions. So did we do the thing with the microphone here? All right, questions, anybody? Don't fire them all off in parallel.
Hi, when you talked about encounter order, I thought that was interesting because I've never thought of it that way. I think probably badly in terms of associativity and commutativity, which I probably mix up quite often. But I ask myself, does ordering affect the result of the computation, and then that as a consequence? But why did you talk about encounter order?
Why did I talk about?
As opposed to those other concepts, is there a subtle difference, or?
So, So I think the question is, correct me if I'm wrong, so I would think parallelism is mostly about, is my combining operation associative and all of that, but you talked about this weird thing in counter order that I'd never heard about. Why? Is that your question?
Yeah.
Okay, so the answer is, most people have heard about the notion of, in order to decompose a problem in parallel, you need to have some efficient way of combining the operation. Most people haven't thought about, is there something intrinsic to the operations I'm doing in my program that are going to undermine parallelism? And parallelism works best when you can divide the problem up into chunks that everybody's operating independently on. Encounter order undermines that independence criteria, right? If some chunk is somehow semantically different to another chunk because it comes earlier in the decomposition, then that means they're not really independent, and that limits how much parallelism you can get. And it's some of the worst examples that we've seen where people say, I tried to run this in parallel and I got a terrible result, was when you combine something like limit and find first, right? So limit and find first are both encounter order sensitive operations, and they actually interact really terribly, but they work great sequentially. So we have all of these years of sequential training to think, all right, well, limiting, really cheap operation, finding the first element, really cheap operation, must parallelize great. Actually, it parallelizes terribly, right? And so this is counterintuitive and surprising, and so I'm kind of here to talk about the things that are counterintuitive and surprising, because the other things are kind of obvious. So we have time for one more question. Maybe, maybe not. Yes, we have time for one more question. Question in the back, sir.
I was just wondering if you could spend a couple of minutes talking about the JVM warm-up to get best performance from streams and parallel streams.
Yeah, so the question is, how does JVM warm-up play into this? And warm-up isn't a single thing. Warm-up is a lot of things. Warm-up involves class loading. It involves compilation. It involves initializing JVM data structures. And using parallelism also has an element of warm-up. What threads is your task going to run in when you run a parallel stream? Well, the library spins up a common fork-join task pool. And that involves creating some threads. So the first time you do a parallel operation, it's going to go and look to see is that pool started, and if not, it'll go start it, and it will start some threads. That's going to be slower than if that pool is already up and running. So typically, the threads in that pool will stick around for some amount of time, a minute, a few minutes, et cetera. And if there's no work to do, they'll tear themselves down so that they don't sit around using up memory. And so just like all the other aspects of warm-up, there's a warming up the parallel subsystem that largely involves starting up threads. Similarly, within each task, there's a little bit of micro warm-up of getting your data into the cache, right? So if you get scheduled on one of these threads, whose data is going to be in the cache? Well, the previous tasks. Hopefully, your data exhibits good locality, and you'll be able to benefit from, you do a little bit of work to warm up the cache, and then you get good performance out of it, but that depends on locality. So there's warm up at many levels. So I think that takes up our time, so thank you very much.